Let's move on to our next topic. And the next topic is rightmost and leftmost derivation. All right, so we are sticking with our earlier example, the same example, and I have kept the parse tree here. I'm going to write the derivation process one more time, but I'm going to do a duplicate here. So I'm going to do it in two different ways. So first of all, we have our two start symbols for our two processes. And just like before, we are going to expand it with the production rule that E can be replaced with E plus E. Now, this is where things are going to be different for the two processes. On the left hand side, I'm going to expand the left E and in this example, I'm going to expand this E. All right. So in one case, I have got the terminal number and plus E. In this case, I have expanded this E instead of this one, and I have got the expression E multiplied by E. On the next step, again, I'm in this case here, I have only one variable, so I have no other choice but to expand this. So I'm going to expand this E. In this example, I'm going to expand the rightmost E. So this is giving me these two strings. And in the next step, here again I'm going to go with the left one. Here again I'm going to go with the right one. So this is giving me these two strings, and as you have guessed, well, in this case I have only one variables in each of the cases, so I'm going to expand those variables. Okay, so as you can see, both these derivations correspond to this parse tree. If you draw the parse tree from this one, you're going to get this parse tree. If you draw a parse tree from this derivation, you're going to get the same parse tree. But in this case, the order is different. In this example, I am always choosing the leftmost variable to expand. All right, so here out of two variables, I'm choosing the leftmost one. Here out of one variable, I'm choosing the leftmost one. Well, out of one variable, you have actually no other choice. Here again, out of two variables, I'm choosing the leftmost one, and so on. Here, I'm just choosing the rightmost variable each time. So as you can see, the rightmost one here, the rightmost one here, rightmost one here, and the rightmost one here. So quite naturally, these two derivations are called the leftmost derivation, and the one on the right side here is called the rightmost derivation. So we have got two more definitions. So the leftmost derivation is when, while deriving a string, at each step, at each sentential form, you are always choosing the leftmost variable to expand. And similarly, when you are choosing the rightmost variable to expand, you are getting the rightmost derivation. So one interesting thing here is that for each parse tree, there is one unique leftmost derivation and one unique rightmost derivation, and vice versa, which means for each leftmost derivation, there is one unique parse tree, and for each rightmost derivation, there is one unique parse tree. So basically, these three things are kind of equivalent. If you get a parse tree, you are guaranteed to get a leftmost derivation and a rightmost derivation. Similarly, if you get a leftmost derivation, you can always just draw the parse tree. All right. So moving on to when we have two leftmost derivations of the same string. As you can see, here we are generating the same string using two different derivations. But these two different derivations are just, we are changing the order of the variables, right? But sometimes you can generate one string using two different ways, while you are in both cases you are using the leftmost derivation, and we are going to see this exact same example using this exact same grammar in our next slide. So right, so we are trying to generate this string, and this is our first leftmost derivation. We are expanding E using this grammar, this production rule. We are producing the plus sign first, then changing E to num, and then we are changing this E to a multiplication sign, just as we saw in our earlier slide. On this side, however, things are a little different. So instead of expanding the start symbol, using the production rule E plus E, we have expanded it using the production rule E multiplied by E. And then we have chosen the leftmost variable to expand that to produce E plus E. And then we have went along in a leftmost fashion to produce the same string. You will notice that both of these derivations are leftmost derivations, but for the same string we have got two different leftmost derivations and equivalently two different parse trees. When that happens, we call that an ambiguous grammar. All right, so if we have more than one leftmost derivation, or more than one rightmost derivation, or more than one parse tree, which all of three are basically the same thing, we call that the grammar is ambiguous. All right, so that's one more definition for you, ambiguity. Okay, so let's move on and see one more example. So this is the grammar of balanced parentheses, which means the first brackets, but they will be valid strings of first brackets. These three are all examples of valid strings. These are just separate brackets. These are nested. This is even more nested. These are not valid because, as you can see, we have bracket openings here, but no closing brackets. In this case, we have two opening brackets, but three closing brackets. So these two are not valid strings. Okay, so this is the grammar for producing balanced parentheses. And as you can see, this is one leftmost derivation to produce this string, the first example. This is another leftmost derivation which produces the same string but uses a different leftmost derivation, which means two different parse trees or two different leftmost derivation and equivalently two different rightmost derivations, which means this grammar is ambiguous. Now, a side note here, if I ever ask you to tell me if a grammar is ambiguous or not, what you have to do is that you have to find a string for which there are two different leftmost derivations using the same grammar. So if you can show me that there are two different leftmost derivations or two different parse trees for a single string using that grammar, you can tell me yes, that this grammar is ambiguous. The point of choosing this example here was also to mention that the property of ambiguity is a property of the grammar and not a property of the language. So this is the language of balanced parentheses, and this is one of the grammars that describes this language. The ambiguity we are seeing here is a property of this grammar and not this language. I'm gonna show you what I mean. So if I change this, okay, so the ambiguity came a lot later. Anyway, so if I change the grammar to this grammar is a little more complex, but this grammar expresses the same language. And now, if I want to derive this string, we have only one way. In fact, using this grammar, there can be no strings which can be derived using two different leftmost derivations. And this grammar is not ambiguous, which means the same language was ambiguous a little while ago, but right now the same language is not ambiguous anymore. As you can see, not ambiguous, which means the ambiguity is a property of the grammar, not the languages. Of course, you can find some languages for which there will be no grammars which are not ambiguous. All of the grammars for that language can be ambiguous, but still the ambiguity is a property of the grammar and not the language. For example, let's look at the next slide. In this case, we have our language where the language is all those strings which have some 0, some 1 and some 2. The condition is the number of 0 and 1 has to be equal, or the number of 1 or 2 has to be equal, either of these. Okay, so to produce the grammar here, this is also a good example of producing context-free grammars in general. So please put some of your concentration in this right now. All right, so as you can see, there is an or. All right, so we have to maintain one condition or this other condition. So if I want to maintain this condition, what we have to do is we have to produce equal number of 0 and 1. The 2 can be any number I want. And we already seen how to produce equal number of 0 and 1. So for example, all right, consider this string a little later. Let's first look at the grammar. So this is how I generate equal number of 0 and 1. We have already seen this in our 0 to the power n, 1 to the power n example. And b is just going to be 2 star. We have already seen that too. So these two, if I combine them a little later, let's look at this part here. If I want to keep the number of 1s and the number of 2s equal, I have to produce equal number of 1 and 2, and the number of 0 can be anything it wants. So we can also do this. D is going to produce equal number of 1 and 2, as we have seen earlier many times in many examples. And C here is going to produce any number of zeros. C is basically 0 star here, and not 0 star, 0 plus. So 0 plus. All right, so I can have either this or this. I cannot have both. So our start symbol is going to produce a OR relationship between them. So from our start symbol, I can either go this way or I can go that way. If I go this way, I'm going to have this condition fulfilled. If I go that way, I'm going to have that condition fulfilled. I hope that made sense. Now consider this string. In this string, I have equal number of zeros, equal number of 1s, equal number of 2s, which obviously satisfies this condition, both of these conditions in fact. And as you can see, I can produce this string even if I go this route or if I go that route. So if I use this Parse tree or this Parse tree, there will be more leaves and more nodes at the bottom, but those are not important. As you can see, these are two different Parse trees, but both of these trees are capable of producing this. This is going to maintain these two, and this is going to maintain the number of these two. But both of these are going to produce this string, which means this grammar is going to be ambiguous. And intuitively, no matter what I do, if I try to maintain this condition and if I try to maintain this condition, they are going to be two separate ways of derivation. And for strings that has equal number of 0, 1 and 2, there will always be an ambiguity. So this grammar, this language, although we say that language and ambiguity is not a property of the language, but this language will have no grammar which is not ambiguous. All of its grammar is going to be ambiguous. In this case, we say that this language is inherently ambiguous. All right. So still, I'm insisting on this, that ambiguity is still a property of the grammar and not the language. In this case, it just happens to be all of the grammars are ambiguous, and that's basically it. All right.